So far we have seen one type of density estimation, which is primarily a parametric method, and the method that we have seen is MLE, maximum likelihood estimate, where we assume that the underlying density, the form of the underlying density function is known, and our problem reduces to the context of estimating the parameters of the density function. And what we do there is we find the likelihood, write the likelihood function, represent that in a log likelihood form, and try to maximize the log likelihood in such a way that the observed data, the chance of finding or getting the observed data is maximized when the given parameters are there in the with the model. So estimate the parameters in such a way that the observed data, the likelihood of the observed data is maximized. That's called the maximum likelihood estimate. That's a parametric model. The other class is called non-parametric classes, where you don't know, right? There are arbitrary distributions. I don't know the form of the distributions, and we don't make any assumptions on the form of the distribution, right? Underlying density functions are unknown, and we don't have any idea on that. How do we proceed in such cases? And we have seen a very trivial case. That's where we started in a univariate, in a single dimensional case. There's a single variable. What we can do is we can potentially look at things of the kind histogram. This is essentially a counting based technique. All right, you divide your data, the range of the data falls into multiple bins, and then you count the number of times the data points, given set of data points falls into these bins, and then represent that. And if you have a larger bin size, you get coarse representation, and if you have smaller bins, you get fine grained representation. Your curve will be more smooth. But if you reduce that to the level of a point in a bin, then it essentially equivalent to fitting your what you call data into the most granular fashion, which may not be also a very good idea. All right. So the baseline is histogram is a way to count. When you have non-parametric context where you don't know the form of the distribution, the baseline is, can we count? How do we count? Or are there mechanisms to count and represent the notion of density, right? And let's look at a little deeper into the theoretical framework, right? This is little involved math, but make sure that you understand at least the crux of it. We'll come back to it at a later point in time if we need a little more clarity. So density estimation, we are essentially, this is non-parametric density estimation, where you don't know the form of the distribution, you don't know the structure of the distribution, right? All you know is you're given a set of data points. How do I estimate density, right? So probability P that a vector X will fall into region R can be represented over X is basically integrated over the region R. Px dash dx. Basically, Px dash is your understanding about the density, and over the region you aggregate. That's what it is. All right. And if I've got n IID sample, in our case, we are asked to estimate the density from the given identically distributed independent data points. All right, and samples are X. And how do you do this? How do you estimate the density? So given IID samples of X, the probability that K of these falls into R, the region R, is given by the binomial. Essentially, like if what do you call it, given n, K falls into the region. If that's the case, K can be chosen out of M, and P is a chance, is a success probability of a point falling into the region, and 1 minus P becomes what do you call the failure rate. Then n choose K, P rise to K, 1 minus P rise to n minus K would become the binomial representation, binomial distribution for this particular context. All right. And the expectation of binomial is we need a P. It's basically like what you do is XPX summed over all the x's, possible x's. So the expected value of K would be n into P. All right. That's trivial for a binomial, a trivial understanding from a binomial distribution. So expectation of K is n into P. which means that k by there are like kind of, now we have pk, and like expectation of k is n into p. So which means that if I have k points, k by n can be an estimate of p, right? That's what it says. Expectation of k is n into p, which means that p can be estimated as k by n, provided we have large enough number of points. The number of points n is large enough, right? That's how you like kind of you take the frequency based estimation of probabilities, right? You get an estimate. So the estimate of p would be, we can write that as k by n. Now you look at the an approximation of integral over r px dx. If px is continuous and in the region r and is so small, p does not vary. So basically, there is sort of a uniformity around the region r. All right. If we, then in that case, you can write the px into v. Right. V is a volume. V is a volume enclosed by r. V into px would be the primary what do you call, the is an estimate of capital P, which is essentially like the probability that a vector x falls in a region cumulative over the region R. Right? The cumulative over the region R can be approximated to Pxv. So you get two equations, P is equal to Px into V, and where P can be estimated as K by N. So you substitute it back. So you get, you can write Px into V is equal to K by N, right? That's what it is. So Px can be approximated as, we can estimate Px as K by N by V. So this is where it starts. This is where the counting starts. I'll go back to the math once again. It's a little involved if you don't have a proper understanding of the notion of cumulative or a binomial distribution. What you do is like the probability. What you complete is the probability P. It's essentially like the probability that the value falls in the region R is Px dx, which is nothing but the typical CDF, the cumulative over the region R. And if you have n IID samples, IID meaning you can actually independent analytically distributed samples, then that's your data, right? From your data, you can find the number of successes. Success you define as the probability that a point falls in the region R. That's called a success. So out of n, k will fall in. N choose k, p raised to k1 minus p raised to n minus k. So there is don't get that the other p getting confused with the first p on the first lines. Is we can even use a small p here. So there is a, so pk would be basically it's represent a binomial form, and the estimate of expected value of k in that case would be, since it's binomial, expectation of k would be k is the number of successes would be essentially np. So that means k is equal to an estimate, expected value of k is np. So an estimate of p would be will be k by n, right? That's what it says. So so the cumulative can be approximated to px into v if p is more or less continuous and it does not vary. So it can be approximated to px into v. That's so px into v is your cumulative, which in turn you have approximated px to be essentially p to be k by n here. So you substitute it back. So what you get is k by n divided by v. So you get a means to estimate the unknown distribution, unknown density px as in terms of what you call a count. Count is you have n set of data points, out of which k is within your context, your interest area, and v is the volume that is under consideration. So if we can define some sort of containers, right, or if we can define the number of points under consideration. So you can, so if you want to do an estimate using this equation, what you can do is, you can do two things. One is I can fix a volume V. Once I have volume V and I know the data points, out of the n data points, success is defined as the point under consideration falls into that volume V. So I can count K, right? I can take K by N as an estimate of P, and K by N essentially will give me an idea on an estimate of the estimate of Px. That's one way of doing it. The other ways, there are other ways of doing it, which is I don't fix V. Rather, I would say, hey, let me get some set of points, a given set of points. Given set of points, maybe like let me take 10 points, and my context of interest is a particular points belong to a particular class. I want to find the class conditional density, or rather posterior density. Basically, like it's basically conditioned on the observations. How do I estimate the class probabilities, which is essentially what we have done in with the Bayes thing, Bayes theorem or Bayes classifier. So how do I, can we forget about V and can we look at K points, and out of which how K is distributed among the set of all possibilities? Can I come out with the notion of a density estimation? And that is another class of algorithms. So the first class of algorithms where we fix the volume and do a counting is called the Parzen window. The second class of algorithms where we fix K and do the counting is called the K nearest neighbor algorithms. Both these doesn't assume the form of distribution. Right, let's get into our agenda, which is Parzen window. How does it work? Again, I told you this is very similar to the histogram kind of concept, extended to n dimension, but again counting based. It's also called this Parzen window approach. The non-parametric approach is also called the kernel density estimation, and the approach is also called Parzen Rosenblatt window estimate. So it's basically after those who have worked on that context. So there is, let's assume that our baseline is Px can be estimated as K by N divided by V. Let's fix V. That's what we do in Parzen windows. If Hn is the length of the sides of a hypercube, its volume can be, it's a d-dimensional hypercube. Hn is the size. If you want a simpler representation, you can call it h to the power d, h rise to d will give you the volume of the hypercube. We index that with a small n. So Hn is the length of the side of the hypercube. Its volume is given by Vn. The volume encompassed by the volume of that hypercube would be Hn. N is the index, Hn to the power d, right? We can obtain an analytic expression of K, the number of samples falling into the hypercube. Now what we do, we have a hypercube. What we can potentially do is we can find, all right, the number of points that are falling into the hypercube. I can start counting, right? We can obtain an analytic expression for K, the number of samples falling into the hypercube, by defining the following window function. I'll define a window function. Window function is essentially like, when do you say that point is inside or point is outside? Essentially, I am defining the notion of success or failure, right? That's what the window function is with respect to the hypercube, right? With respect to the volume, with the volume occupied by the hypercube, can I define the notion of success or failure, right? It's essentially counting. So phi of u is essentially, I'll say it's 1 if it's less than half, less than or equal to half. The distance is basically like less than or half, or otherwise it's 0. That's phi has the value 1 inside and value 0 outside the unit hypercube, centered as the origin. So essentially what we do here is, now I have a hypercube. If I can fix the if I know the center of the hypercube, I can say whenever a new point is here, if the distance of a given point from the center of the hypercube is less than half of the length of the hypercube, I would say the point is inside, right? Otherwise it's outside. That's the basic geometric interpretation. All right. So phi of x minus xi, all right, by given hn is equal to the if the unit if xi falls within the hypercube, then we call that, we say that it's a success, which means that we can count it in. If h is greater than 0, it's called a bandwidth parameter. Primarily h is essentially like you are placing a hypercube centered at x and say if a given point x, right, the distance of the given point xi from x would be xi minus x. You can define the notion of a distance using, say, for example, Euclidean. And then if the distance is like less than half of the length of the hypercube, what will happen is the point is inside the hypercube. Let me repeat. In this Parzen window, we define the notion of a hypercube. The size, the length of one side of the hypercube is h, and the center of the hypercube is x. So for any point, you can find, for any point xi, you can find the distance between the point xi and the center of the hypercube x. If that distance is less than half of the length of the hypercube, you know that the point is inside, which is called a success. Otherwise, the point is outside. And the window function is nothing but a function that defines that. If the distance is less than half of whatever, right, it's basically like half. If I assume that h is equal to 1, half, that's a basic definition. So you can assume that the hypercube is centered at 0 0, right, or 0 0 0 in the case 3-dimensional context, and the length of the hypercube is 1 if the distance, essentially u, the point j from the point j, the distance from the center to the hypercube is less than half. Half is essentially like half of the unit length hypercube, it's half. Then you say like it's inside, otherwise outside. Generally it's h by 2. So you write phi of x minus xi. If it is less than h by 2, you say it's 1. If phi of x minus xi, that distance is, otherwise it's not less than or equal to h by 2, you put it as 0. So essentially you're counting whether, you're checking whether the given point xi with respect to hypercube centered at x and a side, the length of a side h, is it inside or outside, right? So what you do is you count it, and once you have it, you can actually count the number of samples in the hypercube. It's essentially kn would be over all the points given phi of x minus xi by hn, essentially like kind of, if it is inside, you get an estimate, all right? Say for example, Pn of x can be estimated as, now you know that Pn of x is your equation kn, essentially kn is that small n is essentially the index, k by n divided by v. That was the equation that we have here, k by n divided by v. So now you have an estimate of kn, all right? Kn is, so you take out n, and vn, you know that it's h to the power d. So 1 by n into summation I is equal to 1 to n, 1 by vn, phi of you substitute kn there, and you get an estimate of px. So baseline, all right, what do? You construct hypercubes of size h, all right, and I've got n points. These hypercubes define essentially your windowing function, and essentially what you do is you count, you treat the case where a given point falling within the hypercube centered at x as a success, and otherwise it's a failure. You call it 0, you label it as 0. So you count the number of successes as the number of points falling within the hypercube out of the given set of n points, and then you know the volume of the hypercube. Then you have everything, right? All you need is k you get from counting the number of points inside the hypercube. N is your given set of points, and v is the volume of the hypercube. You can actually compute you can actually estimate. Pnx estimates px as the average of functions of x at samples in 1 to n, estimate is an average over the window functions. Usually the window function has its maximum at the origin, and values become smaller and smaller as it goes away from the origin. I'll show you an example of using a normal Gaussian function as the windowing function. Let's see a numeric example. This will make your life a little more easier. Concept is again, the baseline concept is counting. To count, this is your estimate. While doing the estimate, you need to count. I can count by fixing the volume. That's Parzen window. V is fixed. V is nothing but a hypercube, right? Let's look at this context. Given the data set below, using Parzen windows to estimate the density Px at y is equal to 3, 10, 15. Use a bandwidth of h. Bandwidth is essentially the length of the Parzen of the window is called the bandwidth. So you've got points there, right? So this is just what you call a pictorial of the representation. You have got the data points represent over the space. Right, how many points you have, and I need to estimate the density at 3, 10, and 15. That's our agenda. And all right, and I repeat, the use of the word density is not proper, because essentially like the moment the point-wise estimate of a density would be a continuous distribution 0, but yeah, we're essentially talking about mass functions. So y is equal to 3, y is equal to 10, and y is equal to 15. You have got the points put out there. Window function is, we define the window function as, so we define the hypercube as a hypercube with what you call bandwidth is 4, and the other one, right, the centered at 0 is our origin. Let's now estimate Py is equal to 3. How do you estimate the density at y is equal to 3? So Py is equal to 3. I need what you call, I need multiple things. I need the number of points. I have the number of points. How many points I have? I have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? I've got 10 points. Right? And my window bandwidth is basically like the window size is 4, or the length of a window is 4. It's a unidimensional. It's basically a single dimensional data. So so you get the volume as h raised to 1, right? So basically 4 raised to 1. So you have that, all right? Look at this equation. It's essentially like kind of n into Vn. So you get Vn is 10, V is h raised to 1, right? It's 4 raised to 1. And now you need to like you need to look at the window function. This is a window function. Essentially, like window function is nothing but the Parzen windows. Definition of the Parzen windows. The window, now we know that the window is of size 4. So essentially, like the window size is 4. So what you do is you have to compute your window is basically like, so your estimate is at 0.3, right? Estimate is 0.3, right? 3 minus 4, so that will become the first one. So xi is 4. So window centered at 3 is what you look at. Window centered at, so essentially what you do is you place a window at 3. 3 minus 4 divided by h. So you get 1 minus 1 by 4. Likewise, you get everything, right? You get 3 minus 5, again 3 minus 5 by 4, 3 minus 6 by 4. Essentially, you're computing this window, this particular window function. You compute the window function and you get values for it. It will be minus 1 by 4, etc., etc. And you have defined the window function. Window function is equal to 1 if it's less than half. So essentially, your window function is defined as centered around the point. The centered around the point, it's basically the point at which you do the estimation, and the length of what do you call it? The length is less than half. Essentially, like if you're less than half is essentially what you do. What you do is see, you're computing x minus xi divided by 4. Essentially, you're seeing whether what do you call, whether the point is is halfway, like if 3 is the center point, right? From 3, how far is the new point? 4, all right? And then if it is less than halfway, you know that it's inside, right? Less than halfway, it's inside. So 3 by 4, so what you do is 3 minus 4 by 4, essentially like you are seeing whether it's within the window or not. If it's within the window, what you do is you put 1, it's essentially counting. And this 0.5 is actually like, so it's basically 3 minus 4, 3 minus 5 by 4, essentially like in a window of that unit sized window, it's outside, right? 3 minus 4 by 5, it's essentially like you get a minus 1 by 2, it's 0. So you don't get all these points inside, and you get an estimate 0.025. Likewise, you can do it for other positions also, right? At which you need to estimate px. So if you look at this particular calculation, what you see is Parzen window is essentially doing a counting based estimate of density. That's what, where we fix in this particular form, we fix the volume, right? We essentially putting window of a fixed size and then seeing whether your actual given data point is falling within the window, and you can do the point-wise estimations of density, right? That's what it is. That's what Parzen window estimate is all about, right? So this window functions in our case, we had we had this kind of window function where it's basically what do you call it? So the window will will say that it's a success, it's within, otherwise it's 0. You don't have to. You can go for more generic window functions. So you want to estimate to be a legitimate density, we can use something like a Gaussian. So essentially, like if you have looked at the Gaussian distribution, which is also called normal. So what you get is it's a bell-shaped curve, and the bell-shaped curve is a very good choice for window functions. What you can do is you can actually, like, instead of this particular of 1 and 0s, what you essentially get is you can you have the Gaussian case, you have a mean. So you, at your estimate, at the point at which you do the estimate, you place your mean, right? Basically, you assume that being the mean, and then you can find the what you call how far it's from the mean, the given point is from the mean, and always you get a number. You get a number between 0 and 1. It's essentially like the value that you read from the distribution, Gaussian distribution, and that will get whatever, right? Instead of this particular form, that value will be added over here. Instead of a 1 or 0, you get those values, and you get what do you call you get that summed up over all the available points, and then you get an estimate. So it will be a little more generic estimation. This is how it typically happens in practice. You want px to be a legitimate estimate. Legitimate in the sense it's a probability estimate of probability value, so it has to be greater than 0, and it should sum up to 1. Most of the estimations of this kind in using Parzen windows, an ideal bet would be using something like a Gaussian as the windowing function rather than a hard and fast thresholding based function. So, but the problem here is when you are looking at something like this, a hypercube, you know, like the volume that encompasses, right? And the natural question that you come to your mind is, it'll have, say, normal will have long tails on both ends, right? So the geometric interpretation of what is that what do you call that size of length of the hypercube? Yeah, that would be difficult, because I mean, I like enough. We can assume that it's sigmas, 3 sigmas, etc., but that's not a very realistic assumption. So the notion of h and the notion of v becomes very difficult, in the sense it's we can't interpret it properly if you are going for a windowing function like a Gaussian, right? They are related to the window function, but here it's very straightforward. You know, like it's a window of size 4, and then So you are essentially like kind of the windowing function is around centered around the point at which you do the estimation, and the size of the window is 1. That's what you do, right? But if you're going for something like a Gaussian windowing function, life will become a little more complicated. All right, I want you to go through this, and we'll probably come back to this topic again at some point in time, so that we'll get a little more feel of it. All right, I'll probably ask some of you to come back and present it before the class again. So it's straightforward. All I want to show here is this is a counting based technique, and the counting based technique has its own implication. So this is where we fix, in the case of Parzen window, where we fix the volume and then do a counting, right? K is counted as points falling within the window, and n is a set of all available points, out of which in the volume defined by V, how many falls in is K and how many points you have is n. K by n by V is a good estimate of Px, is what Parzen window where we fix V. You don't have to go like this, and here you're directly estimating the in the probability values. There are cases where you're not interested in estimating directly the class condition or whatever. It's basically the probability density estimation, but you are interested. So this is this kind of models are also called generative models, where you are trying to find out the distribution from which the actual data got generated. So there is another class of models called discriminative models, where we are interested to discriminate between points belonging to different classes. Your Bayesian classifier is essentially what you do is you're trying to discriminate, right? By discrimination, you are essentially looking at posteriori probability values. So there are cases where posteriori will become interesting, and one such context of estimation is called Canaan. We'll come there. So just let me give a little more into the Parzen window. So Parzen window, what we do is we fix volume, we count the number of successes within that volume, and then based on the number of points, you do an estimation, right? This is an example, and windowing function Gaussian is a popular choice. Window width, how do we select window width? Is if the window width is too large, the density estimation will be very smooth and out of focus. We will not have anything there. It's very similar to your histogram case. It's too small, you essentially, like, your training samples are your true, then you don't have a proper estimate of the density. Rather, you have a noisy estimate because you're fitting into the training samples. Right, you need some sort of what you call compromise between the two extremes. You can't have too wide windows or too small windows. Rather, a good strategy would be you can start with a reasonable window size, and you actually iteratively refine the window size. So h1 can be your starting window, h1 by root n is the number of points under consideration. Then you can hn by, at any iteration you refine it. So this is, you keep bringing the window size down so that you have a smoother estimate. That's one way of doing it. Convergence is a problem. I'm not going to prove convergence for Parzen window here, but convergence is in the mean square sense. What you do is, as the number of points goes to infinity, you want to have the expectation of the estimate should actually converge to the actual. Right? We want to have the correct estimate, and we want the variance to be minimized. So if you look at it, so the MLE case, you're essentially estimating the parameters, right? And then you want the parameters in such a way that your data fits into the context. In the case of a Parzen window, you estimate the probability values by counting. And as the number of points under consideration, you have a lot of samples of training data, then you would naturally expect that your estimate converges to the actual. If that to happen, your expectation has to limit n tends to 0. Expectation should tend to the actual, and the variance should be 0. So correct estimate is interesting, and there are proofs around this. If some of you are interested to go further, if you are if you want to explore Parzen windows primarily from a research angle, this would be interesting. Convergence of Parzen windows would be interesting. I won't be covering that for the class, but we can always look at it offline. All right. Given that, let me move to another. Let me give you a flavor of another estimation technique also. This is again non-parametric, which is originated from this concept of estimating px as counting the successes in n out of the n samples or discrete values that you have, and then looking at the volume. And the Parzen window estimate is primarily about estimating the class conditional or the density. But the next class, the next approach of non-parametric approach, KNN primarily works around discrimination. I'll give you the flavor. I'll just move on to that. K nearest neighbor estimation, which is not there in your outline, but I thought I'll just give you a flavor of this. Goal, a solution for the problem of the unknown best window function. We don't know, like approach, estimate density using real data points. We have data points. Let the cell volume be a function of training data is what, say, rather than fixing the volume, can we fix K, right? That's what K nearest neighbor approach is. So if we have density is high around X, I want to estimate around the point X, what can happen is density is high near X, therefore the cell will be small and provide good resolution, which is possible. So I need K points. I need 10 points around X. I get 10 points within a small volume, and every point is belonging to a particular class. What can I do? I'll say, okay, this is a very dense region for that class. That's what the meaning, right? So, but I'm looking for 10 points around X. I see that I have to this set of points are occupying a larger volume, which means that this cell is not very dense. It's very chaos, and then density is right. I mean, I don't have probably like a dense region, rather a chaos region. So how do we estimate, right? How do we do an estimation of the probability given this kind of an equation is, go back to the equation. This kind of an equation is, there are two approaches primarily. I told you, by fixing V, we have Parzen window. Can we fix something like K, right? And then we count. And this approach, K nearest neighbor, is around that. How does it estimate? We want to estimate the primarily, like, it is an approach for estimating posterior densities, right? Typically, like, I mean, that's not the only approach, only application, but let me explain with a posterior estimate P Wi given X from a set of labeled points. X is the point at which you need to do an estimation. Wi is a class. All right. Let us place a cell of volume V around X and capture K samples is 1. All right. I don't know. I don't fix V. Right. K1 among K samples turn out to be labeled as Wi, which means that out of the K samples I've found out, K1 falls into a particular class. So K1 by whatever, then you can estimate. What I need is K1 by N by V, which is what our estimate is like. So we can estimate the posteriori Pwi given X, essentially like the posterior probability of the class omega I, sorry, I was using the word Wi. So omega I, posterior probability of omega I, the class omega I given X can be estimated as, so this is essentially Pn x omega I, so joint probability of X and omega I together, and overall it's Pn x by, this is something that we have seen in the Bayesian context. So Pn omega I given X can be written as Pn omega X or X omega I divided by the joint probability divided by the by p of x, pn of x. Pn of x is essentially summed over all the classes pn x comma omega j. So this is something that we have seen, and we can see, we can estimate that as ki by k is what k nearest neighbor approach is all about. We'll say, like, out of the k points that I have found out, I'm looking for 10 points, out of which I see that 7 points are falling into the class which is what I'm interested in. Then I'll say 7 by 10 is a good estimate of the posteriori probability of class given the data point. That's a whole idea of a k nearest estimation. Ki by k is a fraction of samples within a cell that are labeled as the class. Right, that's essentially the point. So k nearest neighbor estimation works by, this is not there in your syllabus, just for those who are interested to go a little further. Both Parzen window and k nearest neighbor estimations are counting based techniques, non-parametric. In Parzen window, you fix the window size and count the number of points falling within that volume, which is k, and out of the given set of points n, that's and you directly estimate the class condition or the densities. And there are cases where you are interested in posteriori in the sense you have labeled the data and you have a lot of them. All right, can I use a very similar counting technique leveraging the same principles where I don't fix the volume, rather let me do a counting around a point. Let me fix a k value. I'll say I am fixing a k value of 10, which means that I'm looking for 10 points around me. And if all 10 points, and I'm interested in finding the probability of a class given a point, right? So I have got a point, I need to do a point wise estimation. I have a point around which I fix a k, and fix k is as 10. I would say, let me look for 10 points around me, and out of which, if say 7 points are falling in the class of my interest, I will say a good estimate of my probability of interest, which is probability of the class given the point, can be the number of points falling in that class divided by the number of points that I am considering k, right, which is 10. So 7 by 10 can be looked at, can be seen as a good estimate of my posteriori probability. So there are people have attempted this particular thing in different, this k nearest neighbor estimation, essentially in the case of discriminative approaches used in classification. What you do is you are looking for n points around a point or k points around a point, and then the frequency, I mean, primarily like the frequency, you can count the number of times the required class or the class under consideration falls with, I mean, are present within the points that you're that are under your consideration, which is k. So if k1 out of or ki out of k falls into the class under consideration, a ki by k can be treated as a good estimate of probability of class given data, which is posteriori. So this particular approach is called k nearest neighbor approach, which is also a non-parametric. Just for, and you can read further on k nearest neighbor approaches. This is used heavily in classification, and I think I'll stop my recording over here. So these are the two approaches that are present, that are predominant in the case of non-parametric techniques. All right, the parametric technique meaning where you know the structure of the distribution, MLE, maximum likelihood estimate, where you estimate the parameters of the distribution, and non-parametric techniques is counting based. You can very well presume that to be an extension of your histogram kind of approaches into multiple dimensions. But histogram based approaches becomes very difficult. So what you do is essentially you define, you find methods to count, and the methods to count can be done in two ways. You fix the volume and then count, and if your point under consideration is within the volume, you say like it's a success, and then you can do an appropriate estimation. This is called Parzen window. And if you're fixing the number of points that I'm looking at around a particular point of interest, and then based on the frequency of required of my concept under consideration, I can define an estimation of the probability, which is called k nearest neighbor approach. And these are the primary non-parametric approaches out there. And I stop my recording out here.